introduce the speaker for this session, Guy Bursell. Guy Bursell is a Director of Business Strategy within the manufacturing and supply chain industry team at Microsoft. Guy has 20 years experience working with customers globally in deploying leading industry product lifecycle management solutions, first as a solution architect as well as a product manager, overseeing platform architecture modernization and cloud evolution transformation and support. With a focus on unlocking digital innovation through digital engineering on the cloud, driven by cloud high-performance compute, digital thread, digital twins, and connected product innovation, Guy drives go-to-market initiatives to transform manufacturing-focused enterprises. He also focuses on field enablement and works with the solutions sales teams and partners to drive industry solutions globally. With a passion for enabling digital transformation, Guy brings a wealth of experience from industries, including aerospace and defense, industrial equipment, high-tech, energy, heavy equipment, and machinery, as well as transportation and marine. These industries make up key verticals in the manufacturing industry space. It will now be our pleasure to hear from Guy Bursell.
Hello everyone, I'm excited to be here and thanks for joining me to talk about how Microsoft are empowering and enabling innovation and new opportunities through cloud, high-performance computing, and AI and machine learning across many industries. My name is Guy Bursell and I'm a business strategy lead on the worldwide manufacturing and supply chain industry team at Microsoft, and my focus is on helping manufacturers to innovate. Over the next 20 minutes or so, I'm going to share how combining intelligent cloud, high-performance computing, and AI and machine learning are proving to be industry game changers as enterprises look to unlock innovation, break free of constraints, and embrace agility to get the answers to larger, ever more complex and impactful questions. Microsoft Azure provides a high-performance computing solution that is cloud-based, rather than a cloud provider trying to do high-performance computing. And this is helping to accelerate compute adoption across a myriad of industries. Enterprises are grappling with challenging poles of geopolitical uncertainties, rising energy prices, raw material shortages, supply chain disruptions, skilled labor shortfalls, and the growing importance of sustainability. At the same time, digitalization is wreaking a fast-paced, fundamental change in the value creation process of enterprises and is driving business, productivity, long-term competitiveness, and opening up new opportunities. We've seen cloud-based engineering accelerate computing adoption that is transforming industries. Enterprises are looking to increase innovation, reduce defects in products, improve decision-making, increase their time to market, reduce R&D and production costs, increase collaboration, and accelerate R&D cycles. The technologies behind high-performance computing are helping to enable new usage scenarios. Enterprises want to answer larger, more complex and impactful questions for their solutions, and increasingly AI and machine learning algorithms are incorporated into these solutions. Now, when we think about this from a product development perspective, we see traditional modeling, multi-physics simulation, virtual prototyping, design optimization, design verification and validation, engineering workstations, and data visualization and digital twins. Behind these are really two types of workloads. We can think of loosely coupled workloads that focus on solutions such as autonomous resimulation, genomics analysis, image processing, rendering, or visualization, financial risk analysis, and EDA, where parallel processes or iterations in the simulation are aggregating the results from many simulation runs that together serve to bring to light a novel knowledge about the solution being analyzed. Tightly coupled workloads consist of parallel processes that are dependent on each other to carry out the simulation calculations. These processes iterate together and require communication with one another, each iteration being a single step in the overall simulation. We can think of examples of these types of simulations, such as climate or weather modeling, distributed AI training model simulation, molecular analysis or seismic processing and reservoir analysis in the oil and gas industry, CAE, finite element analysis for crash simulations, and computational fluid dynamic analysis for aerodynamic simulations, for example. We work to focus on the different industry verticals and take into account the sometimes disjointed requirements of their workloads across the whole portfolio of our products and services. This diversity in the workloads filters down to the diversity in the offerings of our compute, networking, storage infrastructure, as well as orchestration tools and services in a broader open ecosystem. Let me put some of this into context, and let's take a look at some examples of how companies are innovating with cloud and Microsoft high-performance compute and AI and machine learning. There are so many examples of how Microsoft's approach to high-performance compute and AI is impacting and transforming industries. And these are just a few of the interesting cases. Many enterprises have invested in on-premises high-performance compute clusters and infrastructure. In addition to upfront capital costs, capacity is fixed, hardware often becomes obsolete very quickly, and this boundary can limit the ability to scale beyond your walls. Hendrick Motorsports took this constraint and were able to burst to cloud to scale in a hybrid model as needed beyond their on-premises hardware and infrastructure, increasing its simulation capacity for computational fluid dynamic simulations by over 35% in only 10 minutes. Rimac Technology builds and sells the Navira, a near 2,000 horsepower electric sports car that can be fully charged in as little as 20 minutes. Designing and realizing such high levels of performance relies on its simulations for core components such as electric motors, inverters, gearboxes, and battery packs. These simulations enable a level of focused and precise data collection that can't be matched through physical testing, where something as simple as a misplaced sensor runs the risk of compromising data or even worse, damaging a €2 million car. Migrating simulation workloads from on-premises to cloud allows them to improve and optimize simulations of models, adding greater complexity to those models and doing it all so much more faster. Ricoh are a manufacturer of multifunction printers. They moved existing on-premises workstation-based CAD and CAE tools in their Asia-based engineering design centers to cloud with cloud-based engineering workstations using GPU-backed virtual machines, and these are accessible by engineers at almost any location. As well as boosting productivity and collaboration, they were able to reduce VDI infrastructure costs by approximately 35%. The IEEE Spectrum estimates that up to 10% of wind power is lost to potential wake effects impacting wind turbines. This was a challenge faced by Vestas Wind Systems, who leveraged large-scale simulation and reinforcement learning to tackle the problem. They applied reinforcement learning to findings from these calculations, employing a neural network to extract optimizations while testing millions of parameters. Even just a 1% improvement has a huge financial impact. In the oil and gas industry, leveraging digital technologies including high-performance compute-based digital engineering and machine learning for game-changing computational science to understand the effects of corrosion in refineries and improve auto lubricants. Democratizing access to technology provides agility for experimental researchers in areas such as sustainable jet fuel. Yes, really. It's jet fuel that's manufactured not from oil pumped out of the earth, but from carbon molecules floating in the atmosphere. And that's likely to become a reality at some point in the future. In pharmaceuticals, the molecular modeling laboratory delivers drug formulation breakthroughs with Azure high-performance compute and AI. While drug formulation has advanced to cater for some pretty remarkable new treatments, humans have often had trouble metabolizing chemically complicated drugs. In response, drug manufacturers use a formulation technique which involves breaking up crystals and blending them with organic polymers to improve the solubility, the dissolution rate, and bioavailability of drug delivery systems. In a global dynamic market environment, engineering company Dive Solutions in Germany realizes ever faster innovation cycles, developing and testing new products for a wide range of challenging operating conditions for e-mobility components such as gearboxes. Moving to cloud-native CAE and computational simulations whilst also meeting their customers' compliance requirements means that instead of focusing on server operations, they can focus on gaining answers to questions like, what happens if the speed of the shafts in the gearbox is 1,000, 1,500, 2,000, or even 2,500 rotations per minute instead of 500? Dane are a German innovation leader that focuses on lightning and surge protection. Now, to stay ahead of their international competition, the company decided to simulate not only phenomena such as voltage fluctuations, but also the tremendous power of full-blown lightning strikes. With cloud, the complexity of simulating lightning strikes was both cheaper and simpler than on-premises. And finally, Vertical Aerospace are pioneers of urban air mobility with a cloud-first strategy with our partners Rescale and Microsoft Azure High Performance Compute, driving a 4,300% increase in performance for CFD simulations, with a 75% reduction in the cost per job. When producing an aircraft, that Vertical said was 100 times safer, 100 times quieter, and at a fifth of the cost from what was previously possible. These successes have one thing in common. Cloud, high-performance computing, and AI and machine learning delivered what would not have been achievable with traditional thinking, IT, and constraints. Azure provides a broad range of capabilities to support the widest variety of compute workloads. But moving high-performance compute workloads into the cloud is not a single destination. Nobody jumps straight to all cloud. There's a spectrum of possibilities, and the right answer varies by customer or even by workload. Whether you're moving a single application into Azure or going to a cloud-native paradigm, there are resources that align with the needs of where you are in the cloud adoption lifecycle. As we listen to and talk with our customers, they tell us they are more concerned about application performance, that is the performance of the calculations or simulation solvers, not the underlying virtual machine performance. And that is a very important distinction to make. More often than not, time to solution is a business-critical differentiator that enterprises are looking for. The diverse mix of workload requirements, characteristics, and demands we've seen in the examples just now require optimized compute SKU designs. These are highly sensitive to performance at large scales of 10,000 cores plus, for instance. The Vestas example earlier exceeded even this scale. Hendrix Motorsport's CFD simulation with Siemens Star CCM Plus scaled using general-purpose virtual machines in scale sets when they burst to cloud. Rimac Technology leveraged HBV3 specialized virtual machines. Ricoh leveraged NC series virtual machines with NVIDIA Tesla T4 GPUs for their engineers who are running CAD applications on cloud-based engineering workstations through Azure Virtual Desktop. Dane also leveraged GPU-backed virtual machines in their simulations. The molecular modeling library deployed Azure high-performance compute and AI resources on more than 18,000 Azure HBV2 VM cores for about 120 use cases optimally configured for high-performance computing with efficient node-to-node interconnectivity, AMD EPYC processors, and NVIDIA InfiniBand-enabled SKUs. So there is a lot to choose from, depending on your needs and workload characteristics. Broadly speaking, a good starting point is to consider some key use cases or categories to explore the most appropriate VMs to use. First, when running CAD, CAM, and CAE design applications on cloud engineering workstations through VDI, The MV series SKUs are optimized for price performance. With the latest in AMD and NVIDIA GPUs, these bring a unique GPU partitioning capability. That means that engineers get the resources they need, and if they only need a proportion of GPU, the cost is just for that proportion. For concept design or rendering use cases, consider the MV and the NC series SKUs. The H and NC series SKUs are designed for tightly coupled simulation and analysis use cases. General purpose virtual machines can be leveraged for loosely coupled simulation use cases. And for deep learning, AI, and machine learning use cases, consider the NC and ND series SKUs as a starting point. Scalability and cost-efficient performance with high-performance compute always comes up in conversations. So I want to take an example and keep in mind different workload characteristics can have different results. The Milan X CPUs in the HBV3 virtual machines delivers extremely high levels of scaling efficiency. The impact of this is significant to Azure customers' return on investment when running these workloads and similar models at scale on the HBV3 series virtual machines. So, namely, there is an explicit relationship between scaling efficiency, in other words, how much time to solution is reduced for each incremental unit of compute, and the Azure virtual machine compute costs. In other words, the billing time for a virtual machine multiplied by the number of virtual machines used. So when we talk about scaling efficiency, there are three types to think of. Firstly, there's the close to linear scaling efficiency, which means performance increases for slightly higher virtual machine costs as compared to a single virtual machine unit of the minimum number of virtual machines that are required to run the problem. Linear scaling efficiency, which is the gold standard in high-performance compute, means performance increases for the same virtual machine costs, while above linear scaling efficiency means performance increases for lower total virtual machine costs as compared to that single virtual machine unit or the minimum number of virtual machines required to run the problem. On much of the public cloud and even many on-premises high-performance compute clusters, close to linear scaling efficiency is considered a reasonable target. Meanwhile, as Azure has often demonstrated, our existing high-performance compute virtual machines are already often able to deliver linear performance increases. This is tremendously valuable for our customers because it means that they can get very large performance increases for flat virtual machine costs. So by pairing the already highly scalable Azure HBV3 series virtual machines with Milan X processors, Azure customers can now realize both dramatically faster time to solution and lower compute costs. As you can see on the slide here, we take the performance information for ANSYS Fluent with the large model to show how Azure compute costs scale with performance increases up to 64 virtual machines, which is 7,680 CPU cores. For this model, strong scaling progressively allows a large enough percentage of the active dataset to fit into memory, which results in scaling efficiency getting progressively higher and higher, ultimately reaching a pretty impressive 200%. But what does that really mean? Well, we can look at it very simply and say for a particularly large dataset, when one Milan X virtual machine instance is used, the cost to complete the task is 1 unit, call it $100. And it takes 1 unit of time, call it 100 hours. With 64 Milan X instances, it takes 127 times less time to compute, say 47 minutes. And since less overall compute time and power was used, it only costs $50. So scaling efficiency does not mean linear increases in cost. Actually, it's the opposite. Key to success of leveraging high-performance compute is having a rich and strong ecosystem. And it is Microsoft's approach to be inclusive towards both the partner and client ecosystem. And we can think about this as meaning really in three key areas. Firstly, market-leading ISVs. Azure is the go-to cloud platform on which the majority of market-leading independent software vendors in the high-performance compute space host their own curated cloud high-performance compute environments for their user base. This has dramatically simplified Azure access and usability for developers that are unfamiliar with high-performance compute, therefore empowering much greater efficiency and productivity without a steep learning curve or several trial and error passes. Secondly, high-performance compute industry partners. Azure has a robust partner ecosystem from hardware partners up through software vendors and systems integrators. Many software vendors work closely with Azure to ensure their applications have really great performance. And finally, think of the HPC application workloads. Azure supports the broadest set of HPC workload types, including structural computer and aided engineering. So workloads like ANSYS Mechanical, Abacus Similia, and LS-DYNA. Computational fluid dynamics, or CFD, with the likes of Star CCM Plus and ANSYS Fluent. Operating system and MPI support from Intel, OSs like CentOS and the Windows platform. Third-party job schedulers, so think of Slurm. Open source toolboxes such as OpenForm for use in CFD, and AI frameworks like TensorFlow. This is not an exhaustive list by any stretch, but I wanted to give you some really indicative workload types. Our mission to empower every person and every organization on the planet to achieve more is a North Star for everything we do, every product choice, decisions we make as a company or as an individual. But this statement isn't just a set of words. When we talk about empowering people, we simply mean that with the right tools, support, and inspiration, anyone anywhere in the world can become anything they want. So finally, I want to touch on how Microsoft worked with ANSYS and leveraged Azure High Performance Compute to bring to life simulation using ANSYS HFSS to enable the Surface device team to quickly iterate on industrial design changes to assess performance that otherwise was not possible without physical prototyping. This simulation process is critical in designing computers, cell phones, and complex radio systems. The accuracy that ANSYS and the Surface team achieved was groundbreaking compared to copper-cutting style prototyping. The Microsoft Surface Antenna and RF team leveraged ANSYS HFSS as a key technology in designing antennas and simulating radio frequency without costly, iterative physical prototyping, working together with ANSYS to leverage HFSS to complete an entire RFIC simulation of a 5.5 times 5.5 millimeter at 5 gigahertz, all under 30 hours. The cloud infrastructure used for this HFSS software run was 704 Intel Xeon cores, working together with no hyperthreading and a total of 2.6 terabytes of RAM. Running on Azure has enabled the Surface Antenna team to reduce simulation time by up to 40% on the most frequent simulation models with this new tool available to the RF designers. And it will really help them keep pace with the innovation that the market demands. I've included a link to the full video interview in this slide, so please feel free to watch. Microsoft don't just provide high-performance compute and AI to our customers, we also leverage it ourselves. So I'd like to thank you all for spending the last 20 minutes or so with me, and I hope you found this session enlightening and thought-provoking. Thank you.